Sometimes one or more functions is described implicitly by an equation such as x squared plus y squared equals 16. We say that's implicit because the y has not been solved for. So you don't see explicitly a formula for y. Now, in this case, we can solve for y to see what function or functions this implicit formula describes. And if you solve for y, you'll get y equals plus or minus the square root of 16 minus x squared. In other words, there's two functions in here. There's the function y equals the positive square root of 16 minus x squared, and y equals minus the square root of 16 minus x squared. It might help to visualize what's going on here. The graph of x squared plus y squared equals 16 is a circle of radius 4 centered at the origin. And the graph of a circle can never represent a function because it flunks the vertical line test. But if you look at the top half separately, that is the function y equals square root of 16 minus x squared, and it just, if you look at just the top half, it passes the vertical line test, so yeah, that's a function. And the bottom half of this circle, which also separately passes the vertical line test, and so is a function, that's the one that's described by y equals minus the square root of 16 minus x squared. So on top you have positive y values, below the x-axis you have negative y values. And this is known as these are known as explicit descriptions of these functions because the y has been solved for. So the formulas explicitly say how to compute y. Now, unlike the formula we were just dealing with, these are not always easy or even possible to solve for y. But we can still find y prime by a method known as implicit differentiation. Let's try it out on our x squared plus y squared equals 16 formula, even though we could go up to our explicit formulas for y and just differentiate in the usual way. But let's see how this implicit differentiation business works. So I'm going to take the derivative with respect to x on both sides of this equation. After all, if the left-hand side is equal to the right-hand side, they must have the same derivative because they're essentially the same thing. So d dx on both sides. Now, before we proceed further with this, really important, we must remember that y is a function of x. So y is not our independent variable that we're differentiating with respect to. It's a function of x. Okay, so let's keep that in mind. Going on, I'll use my sum and difference rule to say, okay, on the left I have d dx of x squared plus d dx of y squared. On the right-hand side, derivative of a constant is just 0. Going back to the left-hand side, d dx of x squared, we can just use the power rule and get 2x. But we have to be careful when we're doing d dx of y squared. See, that x variable does not match the y variable because y is not the independent variable. It's a function of x. That's what we were saying is important to remember up here. Y is a function of x. So I'm going to need the chain rule because this is a composition. The y function is being used as input for the squaring function. So the chain rule says, okay, you can first kind of pretend that you've got something like an x squared and just use the power rule. But then you have to make up for that by multiplying by the derivative of that input function with respect to x. Now this tends to really throw people. So I went off to the right here and did a little example of that idea. So now that we've learned the chain rule, suppose I asked you to differentiate. So I'm over here. Suppose I asked you to differentiate x cubed minus 5, the quantity raised to the x squared power. Well, the chain rule says you can first use the power rule on those parentheses and say I have 2 times, parentheses to the first power. And the chain rule says, but if that thing in the parentheses was not a plain old x, you then have to multiply by the derivative of that inside thing. You have to multiply by the derivative of x cubed minus 5, and you get 3x squared for that in the end. And the way this relates to what we were just doing is I'm thinking of doing ddx of some function squared. It's just that we don't have a formula for the function. That's what makes this all implicit. And so the chain rule says, okay, you can use the power rule on that function, but only if you then multiply by the derivative of that function. And so you're going to end up with 2 times the function times the derivative of the function. So the thing that's different in implicit differentiation is you don't know what y is. You don't have the actual formula for it. You just have to work with it without knowing that. Okay, so we've gotten our 2x plus 2y dy dx equals 0. Now we'll solve for dy dx. I'm going to subtract 2x from both sides. And then I'm going to divide both sides by 2y. So I get dy dx equals minus 2x over 2y. And of course the 2's cancel, leaving us minus xy. And if you prefer, it's perfectly okay to use this shorter notation y prime and say y prime is minus x over y. And that's fine. It's just, I think when you're first learning implicit differentiation, it might be helpful to use the dy dx form to be explicitly saying ddx so that you have a visual that the variable x is not the same as the variable y. So that's kind of a visual reminder that y is a function of x and therefore you need the chain rule. But anyway, if you're okay using y prime, that's okay too. And notice that in the end, we have only an implicit description of y prime. In other words, I don't have a formula for y prime that only has x's in it like we're used to. It's got both x and y.